Charles 2005 defines a big idea as a statement of an idea that is central to the learning of mathematics, one that links numerous mathematical understandings into a coherent whole, page 10. Simeon elaborates and states that a big idea is an idea, strategy, or way of thinking about some key aspect of mathematics without which students' progress in mathematics will be seriously impacted. A big idea also encompasses and connects many other ideas and strategies. For example, any number, measure, numerical expression, algebraic expression, or equation can be represented in an infinite number of ways that have the same value. Page 14, Charles. This is a statement of a big idea. The Programming and Assessment section of my portfolio uses multiplicative thinking as an example of a big idea. Using the number proficiency strand from the Australian mathematics curriculum as an impetus, multiplicative thinking was used as a big idea. This idea then connects to many other ideas, including repeated addition, multiplication, division, place value, and fractions. For example, students in grade 4 will move from repeated addition to multiplying single-digit number and then to multi-digit numbers. And throughout this process, links will also be made to place value and fractions. All concepts, strategies and processes are specific to the intended year level, but are extended and built upon in subsequent years. Therefore, mathematics concepts are not being taught in isolation. However, numerous understandings are being linked as a coherent whole. When considering the importance of big ideas, it is perhaps best explained by Hibert, who states, "We understand something if we see how it is related or connected to other things we know. The degree of the understanding is then determined by the number and strength of the connections." Hibert and Carpenter, 1992, page 67. Because big ideas have connections to many other ideas, understanding big ideas develop a deep understanding of mathematics. When we understand big ideas, mathematics is no longer seen as a set of disconnected concepts, skills and facts. Rather, mathematics becomes a coherent set of ideas. This concept links closely to a constructivist approach to teaching and learning, in addition to my personal philosophy statement, whereby problem solving, reasoning, critical thinking, and the active and reflective use of knowledge are highly valued. It is my aim to continue to provide quality, challenging, and engaging content that will provide students with the necessary skills and strategies to become productive, active members in both the classroom and in their community. Question 2. The 4 important points Marilyn Burns makes about assessment and reasoning are as follows. Uncovering the way students think. Marilyn Burns states that the importance of using questions to present ideas for students to uncover, in addition to providing both oral and written questions to probe students' thinking. Probing students' thinking and incorporating students' reasoning in both written assignments and classroom discussion is an integral part of making assessment an ongoing aspect of classroom assessment. Marilyn highlights the fact that even though a student may get a correct or incorrect answer, it is more important to see the strategies and process the student is using that may be causing mathematical misunderstandings. It is for this reason that class discussions, interviews, and oral assessment should be incorporated in all forms of assessment and class discussions to ensure that all misconceptions are addressed. Assessment through written work. This statement is much more than just presenting written algorithms on a page and assessing the correct answers that are given by the students. Marilyn Burns states that written assessments must be presented in such a way that yields what the student is actually thinking. Within my diagnostic assessment section of my portfolio, I used open-ended questions that required the students to explain how they arrived at the answer and the strategies they used to solve the problem. Through this, I was able to see exactly where the students were having difficulties and any misunderstandings they may have formulated from their previous knowledge construction. By using multiple strategies, students are able to be flexible with their mathematical thinking and look at problems from different perspectives. Number 3. Assessment through classroom discussion. Morrell and Burns states that there are two goals to assessment through classroom discussion. It gives valuable insight into students' thinking and also ensures that all students are contributing and actively participating in their learning. Different approaches to solving mathematical problems are highlighted through this method of assessment, and as a result the teacher may gain insight into any misconceptions or interesting ways of reasoning that the student displays. This assists the teacher when planning for future assessments. By initiating class discussions as a whole group or in small groups and asking the students to articulate their reasoning, the teacher is indirectly saying, "I value your individual approach to solving this problem." This aligns with my personal teaching philosophy, wherein I believe that I am responsible for making the students feel comfortable to ask questions in class and seek help when needed. Number 4. Misunderstandings. So far I've discussed the importance of correcting students' misunderstandings. However, the sole use of written assessments to obtain knowledge of students' understandings and skills can sometimes lead to misunderstandings on behalf of the assessor as well. This was evident to me when completing my diagnostic assessment with grade 4 students on multiplication. The following question was presented to the students. A tap leaks 3 litres of water each day. How much water will it leak in 1 week? I was surprised at the amount of children who answered 15. I initially thought that this was a misunderstanding of their basic multiplication facts. However, further interviews revealed that the students who answered incorrectly considered the days of the week to number 5. They reached this conclusion because there are 5 days in a school week, and because they were taking the test at school, they reasoned that that's how many days in the week the test was referring to. Had I just read the final answer and made my assumptions based on this fact alone, I would have been incorrect, but more importantly, would have made plans for future teaching and assessment that may not have been relevant to those particular students. Question 3. Jones and Albone discuss a number of ways of differentiating learning in the mathematics classroom. One of these ways is to differentiate by task. This involves setting different tasks for learners that address specific learning objectives for the perceived needs of groups of children, while still following a similar theme or topic for the whole class. Whilst differentiation by task seems to cater for all levels of ability in the classroom, Jones and Albone state that poor planning and assessment can deny pupils access to mathematics by giving them tasks which are inappropriate for their level of ability. If the teacher sets tasks that are too difficult, this may lead to frustration and lowering of self-esteem. If the tasks are too easy, then there is a danger of boredom and feeling devalued and unmotivated. Another issue that is raised is that of the selection of appropriate tasks. It is a concern that teachers may inadvertently choose tasks that are inappropriate by not being aware of the previous knowledge and skills that are the foundation of the topic and are required as a fundamental requirement from which to build, and also not having a clear understanding of the likely progression needed to achieve a suitable level of understanding. When considering differentiation through the level of questioning, Jones and Albone state that it is important to understand what kind of thinking a question will generate, and how the question can help children engage with a task. Questions that allow students to access both lower and higher order thinking skills are given to learners during whole class discussions, and cater for a range of learning abilities. Bloom's taxonomy is used to show the varying levels of questioning as it moves through knowledge, comprehension, application, analysis, synthesis, and evaluation. Using this method of questioning, all students within the class are offered the opportunity to utilize their higher order thinking skills, though through slight differentiation of the questions being asked by the teacher that reflects the ability for each student. In fact, studies have shown that pupils learn more in classrooms where the teacher uses a mix of both higher and lower level questions than in those which teachers ask pupils mainly to recall or recognize. Question 4. Go, as cited in Swan 2004, is of the opinion that the best games are those that a child spontaneously chooses to play when time allows. Chess, Scrabble, Ludo and Monopoly are all examples of good games that provide both learning and practice experience. These games are enjoyable to play and involve a great deal of intuitive maths, which is derived both consciously and subconsciously. Games that provide opportunities for spatial thinking, tactical and strategic problem solving are really good games that provide both learning and practice experience. These games can be used to ask children to reflect on their thinking whilst identifying what maths they are aware they are using while they play. In addition to providing games that will allow children to communicate and learn, it is important for the teacher to provide games that are enjoyable, are easily adapted to suit different levels of age and ability, have relatively few rules that can be understood by all players, and that the game isn't too long and has clear mathematical objectives. The game must have a means of self-checking so the teacher is released to interact with the players and observe the learning that is taking place. And importantly, the game must allow for active participation by all students, most of the time. This avoids children feeling left out and isolated, which may have a negative impact on the learning and practice that is being taught through the game. By using games in mathematical learning, children begin to see a very relevant application for mathematics that translates into their real world. Within my mathematics portfolio, I have explained the need to engage and motivate students by providing authentic tasks that extend past the classroom and into their home environment. In addition to the above-mentioned games, games such as chess, draft, go, dominoes, 500, nine men, Morris and Mancala provide a recreational curriculum that advocates the use of games to enhance cultural continuity and social cohesion. Question 5. The Australian Curriculum Assessment and Reporting Authority 2011 state that mathematics has its own value and beauty, and mathematics aims to instill in students an appreciation of the elegance and power of mathematical reasoning. From their earliest experiences with mathematical problems, students should understand and be encouraged to supply reasons for their arguments. Reyes, Lindquist, Lambden and Smith 2009 explain that the NCTM's process standards in relation to reasoning need to incorporate instructional programs that enable students to recognize that reasoning and proof are fundamental aspects of mathematics, develop and evaluate mathematical arguments and proof, select and use various types of reasoning and methods of proof, and make and investigate mathematical conjectures. Two examples of mathematical tasks that develop students' reasoning are outlined as follows. Example 1. There are 11 cats and 3 dogs. How many more cats than dogs are there? The students draw tallies on the whiteboard to represent the cats and the dogs and then explain their reasoning with reference to the tallies. This helps the students communicate their thinking and often results in their solution methods becoming topics of conversation and investigation. Example 2. In the early primary years, creating and describing patterns offer important opportunities for students to make conjectures and give reasons for their validity. In this example, students will develop their reasoning skills by finding the different patterns that can be recognized within this following block pattern. Students are encouraged to explain their reasoning. For example, they could say there's a triangle, triangle, circle, circle, square, square, or there's a small, large, small, large, small, large. Or perhaps there's a thin, thick, thin, thick, thin, thick. Or perhaps the pattern is blue, blue, red, red, yellow, yellow. Two important elements of reasoning for students in the early grades are pattern recognition and classification skills. They use a combination of ways of justifying their answers: perception, empirical evidence, and short chains of deductive reasoning grounded in previously accepted facts. They make conjectures and reach conclusions that are logical and defensible from their perspective. Interactions with both other students and the teacher allow for crucial learning opportunities. The collaborative nature involved in developing explanations that could be understood by others and trying to interpret and make sense of another's ideas and solution attempts as they evolved are a key factor of the constructivist classroom environment, which is the basis of my teaching philosophy. Thank you for listening.